All right, welcome to technical session number 19. We start getting into the fun stuff, talking about TCP/IP protocols and basically how the internet works. So for the purposes of this particular technical session, we're going to be explaining the purpose and role of TCP/IP in the internet or private network. We're going to be explaining the characteristics and properties of TCP/IP and explain common TCP and UDP ports, protocols, and their purpose. For this particular session, we want to keep in mind adaptability. Very, very important in the IT world, as it is always changing, and we have to be able to adjust ourselves with it. And also personal responsibility. We need to hold ourselves accountable to what we say we're going to do. If we say we're going to do something, if we say we're going to help somebody, if we say we're going to be somewhere at a certain time, if we're going to accomplish something, we need to uphold that. But that's just one side of the coin. We also need to take ownership and responsibility of the good things that we do. Because in our careers, in our lives, we are our strongest advocate. And we have to take it upon ourselves to promote ourselves and not rely upon other people to do that for us. Doesn't mean we have to be arrogant about it. The only time I say it is definitely a good time to be arrogant, especially if you're knocking things out of the park, is on review day, when you're sitting down with your boss going over your yearly performance. Yeah, you need to come in prepared with all your stuff and be like, I have done A, B, C, D, E. My progress has been X, Y, Z. The profitability of the company as a result of this has been, QRS. You have it all laid out right there in front of them and they cannot deny it. That also falls under the personal responsibility to advocate for yourself. Hold yourself accountable and advocate for yourself. All right. TCP/IP overview. What exactly is a protocol? Essentially, it is a set of rules that are agreed upon when communicating electronically. There's been kind of like an ongoing joke in the 1,000 or so acronyms that we have to remember throughout this course. If ever you see P, it just means protocol. Almost every single time it means protocol. What essentially is TCP/IP? Breaks down into transmission control protocol, internet protocol. And this is a commonly agreed upon set of protocols that are used to communicate over most modern networks, including the internet. And so on these networks, we have hosts. And so what exactly is a host? That is any machine or interface that participates in a network, whether it is a client or a server. So it is an individual item. It could be a printer, could be a server, could be a computer, could be a laptop, could be a tablet, could be a phone, could be a smartwatch, could be a thermometer, could be a smoke detector, a camera. All of these are considered hosts when they're interacting with the network. So communication protocols, as we have previously stated, protocol is a set of rules that govern network communication. All right, most common one that is used today with regards to network communication is TCP/IP. And it's not necessarily because it is superior, it is because it is the most adapted. For those of us who are a little long in the tooth, you may remember the VHS Betamax fight. And these two competing technologies. Betamax actually was a superior technology, but VHS won out. Microsoft and early Apple, when Apple was first getting started. Apple initially had a superior product, but Microsoft was, where Apple was trying to go for the individual consumer, Microsoft was going for the companies. And so they got all the companies on board, and then people became more comfortable working with the same software at home that they did in their work life. And so they became the most adopted, not necessarily the superior product. Blu-ray versus HD DVD. These Essentially, technological bouts go on all the time. It doesn't matter if you're the superior product. It matters if you are more adopted than your competitor. In this case, it is TCP/IP. Some other protocols that have been used, there was Apple Talk, or Apple, they always get the short end of the stick. Internetwork Packet Exchange, Sequence Packet Exchange, or IPX, SPX. Network Basic Input Output System, otherwise known as NetBIOS. This one does pop up from time to time. And Enhanced User Interface, or NetBUI. So other ones that were there, most have faded away. Some of them still pop up from time to time, NetBIOS being one of those from intranets.
Why they fail?
You what?
Why the others, like, they fail, not use anymore?
It's not that they failed, it's just that TCP/IP was more adopted. And again, instead of trying to deal with two separate protocols, if everybody you're interacting with uses one protocol and you use another, it's just easier for you to switch over and use the other protocol than to have to deal with that interface every single time. So it's kind of how it works. It's almost like at a certain point, there's a tipping point where just the vast majority just start adopting it because it just becomes, well, everybody else is using it. So.
And that makes sense. Thank you.
Mm-hmm. Now, the layers. There's a couple different ways we can look at the networking layers. One of the ways that they like to go through it in A+ is the 4-layer, what they call the DoD model, or Department of Defense. And it is very, very similar to the 7-layer OSI model, or the 5-layer one that Google uses. Where they both are identical is they combine the top 3 layers. The application layer is the top 3 layers combined. So that, because you would only really break these out in more of an academic sense. So from a practical sense, it's okay to combine these 3. And then you have the transport layer, which is the same on both. The network layer for the Google, and the 5-layer or the 7-layer is the internet layer for the DoD. And then the network access layer is the combination of the physical and the data link layers. And then these are the protocols that are being used at each of these layers. So where do these protocols interact with in our systems? This kind of gives you a list. Why do we need to know this? Because if we're having an issue with certain protocols, we know which layers to start troubleshooting at. Makes it easier for us to find and start working. Right? So if I have a problem with my HTTP protocols not resolving properly, I wouldn't go look at my IP addresses or my ICMP packets. So this helps us break it down so that if we're having networking issues, we know which layers are being affected. All right, layers of communication. There's a lot that goes on when you are transmitting any kind of data. So first, you have the application layer where you are kind of inputting the data into the system. It pushes it down into the operating system. The operating system adds components to it so that it can be easier. It is easier to transmit over the network. And as it moves down, more and more things are kind of added on, creating these network frames. And then,
Hello?
Yes. The network card at the very end changes all of this into binary and sends it out over the physical medium, which is your cable or your Wi-Fi or fiber optic or whatever. And then when it gets to the other side, it receives the binary, starts putting the pieces together, and kind of moves everything up the chain. So I have a pretty good video where they kind of break down this happening, what happens to a network packet as it gets pushed through the internet and gets broken down by your computer and then rebuilt by your computer. So it's kind of amazing. All this stuff is happening, and to us, it appears to almost be happening instantaneously. All right. So TCP/IP protocol layers. So we have your application protocol. This is your HTTP. Governs the way the web and the servers and all that stuff and the client interact. So when we go to visit a website, these are the protocols that kind of determine, how that communication or interaction is going to take place. And it allows you to kind of make requests, and it can formulate the responses and go ahead and create exchanges between us and them. We would continually request information. They would be providing information or what have you, and vice versa. So this is all being taken care of at the application layer. And we have our transport protocol, or the TCP. This is the transport protocol that manages all the individual conversations between web servers and web clients. It puts the HTTP messages into smaller blocks because we can't send huge chunks of data over the internet because one, it takes too much time. There's a greater likelihood that the data is not going to make it to its destination. So it has to be broken down into smaller and smaller packets. And then those packets are broken down, sent through, and reassembled on the other end. All right. IP, or Internet Protocol, is responsible for taking these formatted segments, encapsulating them with information that is going to be needed on the other end. So we've sent you huge chunks of data, and how does it get reassembled? What order does it go in? Because with code, if we put things in the wrong order, we can get completely different results, right? So these IP protocols tell them how to package these things so that on the other end, they can be reassembled. And then you have the network access protocols that take the packets from the IP, format them into to be transmitted over the media. And the standards and protocols that govern how these signals are sent, how they're interpreted, what do we need to put on the front end to initiate a conversation so that it knows communication is about to take place? Do I need a response back to say, hey, I got the stuff? Or do I not care and just send it? So that's actually two different protocols. So we'll get into some of that stuff a little bit more as we go, but right now, we got to talk about IP addresses. How do we communicate? How do we talk to each other? How do we know how to get information? Like if I needed to send information to Adebimpe, how do I know how to communicate with her? Where's she located? So we have to use things called IP addresses. An IP address is a unique identification number to any address on a network. And it does two very specific things. It identifies a host and the specific network on which they are located. So an easy way for you to kind of think of this would be the city you're in, which would be your network, and then your street address in that city. So if I just sent out an address or sent out a letter and all I put on there was, 2520 East 3rd Street. How many different cities do you think have an address like that?
Probably a few.
Quite a few, probably. Interesting trivia question. Does anybody know the most common street name in the country?
MLK Street.
Not MLK. It's a good guess, though, actually. I believe that is in the top 10. Huh?
Smith Street.
Smith Street. Most common last name.
Pennsylvania Avenue.
Pennsylvania Avenue? No.
Washington Avenue.
Washington Avenue? No. You can tell the Belters right away. It's actually 2nd Street.
Oh, second, just that's the name.
Second Street, yeah. So it's a number, but it's like Second Street is the most common. But can anybody say why it's not First Street? There's actually a point in time when a lot of First Streets were renamed to Main Street. So Second Street would be the most common after that.
So Main Street is pretty much First Street.
Yes. So, the First Street would either be called Main Street or First Street. So since there is kind of like it's split up, Second becomes the most common name. Weird trivia, just to throw out there, since we're using, kind of viewing this as like a street address versus, a city you're located in. How do these protocols get handed out so that, we can use them on a day-to-day basis? Well, there's an actual agency called IANA. It's the Internet Assigned Numbers Authority. And this is responsible for keeping track of and assigning all IP addresses. So if I need an IP address, a public IP address, I would need to communicate with IANA, request an IP or a batch of IPs, and then they, and I would have to pay a fee for this, and then they would transmit that back to me. And there's two different versions that we can use. There's IP version 4 and IP version 6. IP version 4, there was roughly about 4 billion addresses when they originally created this. They were like, there is no way we will ever run out of IP addresses when they did this like in the 70s or early 80s. Problem was around the mid 90s, we actually started running out of these addresses. So that long ago, IP version 4 was running out of addresses. So we needed a new protocol. 4 billion was just not enough. And not only did we need a new protocol, but we needed a way to buy ourselves time so that we can implement these protocols, because these protocols just can't be rolled out and, flip a switch and you're done. It takes time. We're still in the process of converting right now. And the conversion's been happening for over 10 years at this point. So with that, we have IP version 6. So IP version 4, you had 32 bits that made up that address. Your address looked like 4 little blocks of numbers right here. Each of these blocks between the dots is 8 bits of data. And with those 8 bits of data, we could create numbers anywhere from 0 to 255. So you have 4 numbers that could be anything from a 0 to a 255. We had 4 billion options. IP version 6, we have a 128-bit address as opposed to a 32-bit address, so significantly larger. We began the use of hexadecimals, which we talked about yesterday. And we know that can be anything from 0 to F. Anything above an F is not valid. And our IP6 addresses look something like this. And I'd like to say I don't think we would ever run out of IP version 6 addresses, but the people who created IP version 4 didn't think they'd run out of that. But we would have roughly 320 or 340 undecillion addresses. It's a very strange number. It's 340 with 32 zeros behind it. There are more IP addresses available now than there are grains of sand on the planet. So that's a lot of IP addresses available. So for the time being, it does not look like we're going to need more, but I mean, we're slapping network cards in everything now, from toasters to washers and dryers to microwaves, light bulbs, all that kind of stuff is now getting network cards attached to it. And all those networks have to have an IP address and communicate. So who knows? Maybe in time, we will run out of these. So with these IP addresses, so this group of numbers right here, we're going to be speaking about IP version 4 for a little bit here. So with these group of numbers, we have to be able to identify which part of these numbers identify the network you're in, and which part of these numbers identify who you are in that network. So in order to do that, we use something that's called the subnet mask. So what this does is it's going to tell the routing devices which part of your address identifies the network and which part of your address identifies the host in that network. So the way this looks in binary, if I'm typing out a subnet mask, it looks like this. So this is what it looks like in binary. This is what the computer sees. And basically what this is doing or telling the computer is, if I go back here, stop. If I go back here, you see these dots that are breaking up the IP number? It's telling me that the first two batches of numbers, that 192 and that 168, are part of the network address. So that identifies which network I'm communicating with. So I can route now to the network numbers for the first two parts of the address. The zeros tell me that the last two groups here are the host on that network. Does this make sense? So all the ones are the network, the zeros are the host. Now it's kind of jarring for us to kind of look at this and it make any kind of sense, right? So to simplify it, when we see a subnet mask, it's going to look a little bit more like this. And basically, if you guys remember counting in binary, if we turned on all of the binary spots, it would add up to 255. Remember, that was like the highest number we could get. So if we turn everything on, it's 255. So our subnet mask, instead of being 11111.11111.00000, you know, it's just going to be 255.255.0.0. And then we can look at it and say, okay, the first two groups are network, the last two groups are host. Does this make sense? All right. There's a third way it can be notated. So you have the binary, which we never really see. This is one way that we actually see it. And then there's a third way, and it's kind of basically just adding up all the ones, right? So we know between each dot, there's 8 bits, right? And those bits can either be a 1 or a 0, correct? We call this either a byte or an octet. So if I add all those up, so the first group I have 8, the second group I have 8, so I add those together, I get 16, right? 8 plus 8, 16. So the other way a network can be notated for this one would be a /16. So all three of these things are saying the same thing, that we're using the first two groups of the IP address as the network and the second two as the host.
So the /16, the number there always identifies
The number of bits that
network
you're using.
for the network.
Yeah. Yes, absolutely, absolutely. And that becomes important when we start talking about site or subnetting, which was that quiz that y'all did, and or we're going to skip in the next to the last quiz in module 2 of course 2. So that's way to do it. So now if I have another one here, so let me erase this really quick. Put it down, and I go All right. So if this was my subnet mask, let's see here, Chris, can you tell me another way I can represent that same number? Basically what we just did.
The one on top.
Okay, so another way, yeah, the one on top right here. So I have 3 groups of ones and then a group of zeros. So what's another way I could notate this?
I'll say all three. The first 3, 255, and the last one is 0.
So you're saying 255.255.255.0?
Yeah.
Awesome. That is correct. So that's another way I could notate the subnet mask for that. All right.
So one question. Whenever you see it in that form, as far as the 111, you just have to assume 255, right?
Well, you're never going to see it in the 11111, but this is how the
Okay.
computer sees it.
Okay.
So I'm trying to show you why that number shows up, rather than just saying this is it, just memorize it. Because I don't know about y'all, but I have a better time remembering something if I know why, rather than just, hey, remember this. So Kurt, what's another way we could notate it?
/24,
Why?
because we are using 3 octets.
So I'm using 3 octets, so that's 8 plus 8 plus 8, right?
That's correct.
So I would use /24. That's correct. Thank you. And where you would see this /24 is at the end of the IP address. So if I had an IP address 192.168.15.8/24. That's what it would look like. So that's a quick way of me saying I'm using the first 3 octets as my network, and then only the last group here as my computer identifier as a host. Does this make sense? In a scary sort of way?
Yeah.
Okay.
Yeah. Okay. So.
So the first 3 octets will be 192, 168, and 15. Is that correct?
So I'm sorry, what was that, Jose?
The first 3 octets will be 192, 168, and 15.
Yeah, that would be my network address.
Okay.
So that would identify my network, and then I would be host 8 on that network.
Okay.
Does that make sense?
So host 8, as in the last digits, which is all the zeros.
Yeah.
Okay.
So the last octet here,
Okay, 8.
which would be 8, which you could notate as what? 0, 0, 0, 1, 0, 0, 0, 0. No, I put the 1 in the wrong place. 0, 1. There. So 8. So this would be the binary for my host address. This making a little bit of sense? All right, so we're going to kind of build on it a little bit, but not a whole lot today. All right, and where the IP address comes from is typically when you make a request from IANA, if you're requesting a batch of IP addresses, then they're going to designate what the subnet mask is to you. So they're going to tell you what it is. On your internal or private network, the IT administrator is going to determine what the subnet mask is. So your internal private versus your external public can be two different things. But we're going to get into that. All right, and here's the beautiful part. Based upon our IP address, even if we do not know the subnet mask, we have not seen it, we can figure it out based on what the IP is. So just based upon the number you see, you can tell right off the bat what the subnet mask is. How can we do this, you say? There's a fun little chart. So remember we just talked about this notation, 255.255.0.0 also equals /16, 255.255.255.0/24. We just went over this. This breaks them up into what are called classes. So you have, the ones that we really need to be aware of are class A, B, and C. And each of these classes have ranges for the IP addresses. And this is the range of the first octet. So we had the 22.168.15.8. Which class would this fall into?
C.
C.
D.
C, right? So right here, first octet falls into 192. 192, first octet, right? Yes, if your first octet was 161, you would fall under class B. So if I have a 10.193.251.165. What class would that fall under?
A.
A. Do we need to memorize these ranges? Yes.
Yes.
Okay. So we're going to kind of get into why it's important. And there's more information coming that's going to make more sense. This is a great one to take a screenshot of, just to have for your study notes. So A, B, and C are your most common. D is used for multicast networks. So if I was a company doing a presentation to hundreds of people and we would share this link, we would use a multicast address. And then E is typically used for reserved and experiment. So that's typically government, military, and university use. And yes, it does come up on many tests, Andre, but it also comes up a lot in real life.
Can you
right.
give us example of multicast network other than this?
I'm sorry, what was that, Majid?
Can you please repeat the D class?
Multicast, that would be like broadcasting from one specific address to a multitude of others. So, like the way I always kind of view it is a company doing its quarterly earnings report to all its shareholders. So it's not really a two-way communication so much as it's, you broadcasting to a defined group of people. Does that make sense?
Yes, thank you.
Okay, it's not the same as a broadcast. So a broadcast would be basically sending it to everybody on a network. But it's a multicast, so it is from a single source to a defined group of others. All right, questions on this? So 1 to 126, then 128 to 191, 191, 192 to 223, 224 to 239, 240, 255. There seems to be a number missing here. Does anybody know why? Or have a guess as to why?
Is it 0?
So we have 1 to 126 and then 128 to 191.
127 mixing.
Oh, 127.
127 is missing, but you're right on 0, Chris. That is an absolutely great point. I'll speak on that in a second. So 127, it is the loop back address, right? That's what we use to test our network card to make sure it's working. So that is removed, even though that is what it would be considered a Class A address. So it's a loop back test. And then the 0, Chris, which is a fantastic point. If I log in and I have zeros across the board, it means I have not been assigned a network yet. So that's basically what the zeros mean. So if it's zeros across the board, I don't have an IP and I can't communicate with the DHCP server, and nothing else has been done at that point. But there is something that our computer automatically does to correct for this, but we'll talk about that in a few minutes. So here's our Class A, B, and C networks. We want to drill in just a little bit. Class A's, these are massive networks, okay? They have 16 million possible hosts on their network. Massive. You're talking about some countries, you're talking about Google, you know, you're talking about Comcast, massive networks. Because they're massive networks, there aren't that many of them. There's only 126 of these types of networks total. That's it. So from our perspective, if we're thinking about this, think about this like mega cities. Manhattan, Atlanta, Chicago, LA, Miami, massive cities, millions of people, right? So we're going to need a lot more addresses in those networks to be able to identify individual users, right? Then we get to Class B. 65,000 hosts on each network, right? That's still a lot, but that's not 16 million. So there's 65,000 on each network. There's about 16,000 of these networks. So these are like your mid-sized cities. These are going to be like your Jacksonvilles, your Dayton, Ohio's, your Indianapolis, Indiana. They're not massive metroplexes, but they're not small towns either. But there's a lot more of these little mid-sized cities than there are the giant metro areas, right? And then lastly, we have our Class C. These are like your small little towns. Havana, Florida, Cairo, Georgia, Perry, New York, Evansville, Indiana. Only about 254 people on it because we only have that last little 8 bits, right? So we can only go from 0 to 255. And we have to reserve 2 numbers, one for the network and one for the broadcast. So that only leaves us about 254 hosts on each of those networks. But there's a heck of a lot of these little cities all over the place. So we have about 2 million of those. So that's your difference between your Class A, B, and C.
So these classes, they also classified in geographically, like in the world I'm talking about.
IP addresses can be set up geographically, and they typically are to a degree. But typically it's the size as to what's going to determine them. And that's when we come back here, is if you see a low number, you know it's a giant network.
So I'm just curious, like the Class A IP addresses, can I see the same addresses in Asia or other continent?
Well, they do have some Class A's over there, but here's the thing, is it has to be globally unique. Your public address has to be globally unique, because if 2 networks try to communicate at the same time, or 2 addresses try to communicate at the same time, it doesn't allow it. So one of them essentially gets cut off while the other's communicating. So your public IP has to be globally unique.
Okay, thank you.
Now, private IP addresses that we use internally on our network, totally different story. but we will get into that here in just a couple minutes. So is this making sense? So the blue part of this, so each of these little chunks is a octet or 8 bits of our IP address. The blue represents basically the cities or the networks that we're in, and then the red represents our address on either that network or in that city. Right? Okay. So public addresses have to use the IANA assigned public IP that are given. And that's usually received from either from your internet service provider or IANA. They usually reserve them for internet service providers because they can hold on to those massive sets of IP addresses and break them down into smaller and smaller and smaller chunks for us to use. And the first octet, like we were saying, is what classifies that. And I'll show you here in a minute where that number is coming from too, because it starts to make a little more sense. To me, when I first was in it, these numbers looked very random and arbitrary, like why are we doing this? And then when I got into networking and I started understanding exactly where these numbers came from, it made a heck of a lot of sense. It's not random at all. It actually has very much to do with your IPs, with your IP address and how they look in binary. So first octet breaks everything down like we just saw. You had that picture, it told you all of the stuff, class A, B, and C, and we discussed the network sizes already. Now, in each of these classes, we actually break out what are called private address groups. Private addresses cannot be routed over a public network. And I'm willing to bet every one of y'all, if you ran an IP config, or I'd say 99% of y'all, if you ran an IP config, you would have an address in one of these ranges because your ISP would give that to you from your router. So what it is class A, they have a range between 10.0.0.0 to 10.255.255.255. Gives you your default subnet right here. Class B, 172.16 to 172.31. Class B as well. This right here is called the APIPA address, 169.254. We'll talk about what that is here in a minute because it has a very specific purpose. And then the class C, which tends to be the most common, which many of you will probably have, unless you have Comcast, then you may have a 10, which would be 192.168.0.0 all the way up to 192.168.255.255. So these can only be routed inside of a network. And why that is like I was saying before, we ran out of IPs back in the 90s. Mid to late 90s, we ran out of IP version 4s. So we had to start using something called NAT, or NAT. N-A-T. NAT. And this is called Network Address Translation. So basically, I have a router right here. And I have a external IP of 205.15.72.9. Internally, my router's address may be 192.168.15.0. So depending on where I'm looking at the router from, if I'm looking at it from inside my network, it'll say my gateway address is 192.168.15.0. If I'm looking at my router from the outside, The address is 205.15.72.9. So what's happening here is internally we're using a certain group of numbers to communicate with each other. And inside this network, say we have like 35 computers all talking with each other, going out and visiting the internet, doing all this kind of fun stuff. Well, we're not all talking at the same time, right? So we don't necessarily need 35 public IP addresses to be able to work on the internet. We can actually share one. So all 35 of us internally will have a singular IP address externally. This allows us to save IP addresses, so we can have more hosts working on networks, but using fewer and fewer IPs. And it doesn't matter if at Justin's network at home, he has the same addresses, because that's his private network. It's not going out over the public interface. But on my private network, I can have the exact same addresses inside my network because I'm not going out over the public net. So they're not going to interfere with each other. But when I try to communicate, say, with Google, I send a packet to my router, and my router strips off the IP, my IP address, takes it off, and then it puts its IP, its public one, on my packet and sends it on to Google so that it can go over the internet, the public internet. Google grabs it, gets whatever information I requested, sends it back to me or to my router at this address, and then my router takes it, pulls its IP off, slaps my internal IP on, this 192, back onto the packet, and then forwards that internally to me. What it's doing is it's translating the IPs so that we can use more hosts with very few public IPs. Does this make sense? Conservation of phone numbers, essentially, or network numbers. And this is what network address translation is. This was a very, very clever thing that they did when they started running out of IPs and they didn't quite have the new protocols yet. So what they do is they just reserve little batches of IP numbers to be used strictly internally. It cannot route over the internet. Do we need to know these ranges? Yes, we do.
I'm a bit confused.
What's your question?
So NAT is the one that I guess transforms the internal IP to the external IP, right?
Correct.
So why do you need that range if it's going to be translated anyway?
What do you mean, why do I need that range?
So you know how class A is 10.0.0.0 to 10 dot, and then whatever it is at the end.
Yeah.
Like the range seems small, and I'm wondering what.
With this range?
Yeah.
In this range, I could have 16 million computers inside of a single network. So if we go back here, so it seems like it's small on the surface. When I come here and I have that just the 10 in this N network, I could have 16 million hosts inside that one network.
Okay.
Does that make sense?
Yeah.
And even this network, you know, for most small to mid-sized companies, you're not going to exceed this. That's 254 hosts on a single network. And that's the smaller ones.
Okay. And so there's no similar or like a copy of an external IP in the world then? Would that be fair to say?
They're supposed to be globally unique, yes.
Okay, but a copy of a internal IP can exist, but because of NAT, it's okay.
Well, what it is, so, you know, how many apartment buildings do you think have a apartment 1C?
A lot.
A lot, right? But
Yeah.
it's okay because they're in different apartment buildings, right?
Yeah.
So I would have to get to that apartment building first to be able to get to apartment 1C.
Okay, I see.
So publicly, I have to get to that specific network before I can hit that internal address.
Okay.
Does that make more sense?
Yeah, it does.
Okay. If I make it worse, like if I explain something, it makes it worse, just tell me.
No, that was good.
All right, so building on that, 205.15.72.9, that's coming
Mhm.
from the ISP to my specific router at home.
Yes. So the ISP has like 16 million addresses, and they're just assigning you one of those addresses because you're in their network. This is where it gets kind of funky because you travel to their base, essentially your ISP, before you go out into the internet. So you're inside their network, so it's a different layer, and that's what they assign you.
Got you.
All right. Should
So-
we kind of
so-
wait? Go ahead.
So pretty much everyone on that network externally has this IP, the 205.15.7.2.9, right?
Yeah. So from publicly viewing
Publicly,
any
okay.
packets that come out of there, no matter who sends it. So like if we were all in a network, if you sent a packet out, it would have this as its IP. If I sent a packet out, it would still have this as an IP, even though internally your IP may be 192.168 68.15.27, and then I'm 192.168.15.92. So you send out a packet, it's, and it goes into the router takes your IP off and puts the external one on and sends it out.
Okay, yeah.
So that's what it's doing, is it's pulling off that IP, those IP numbers from your frame, and then putting theirs on and then just forwarding it out. And that's what it's doing. It's just translating the IPs. And then it has to wait to route it back to you once it comes back. And they use what's considered a clever use of ports, which we'll get into in a little bit. And that's how it figures out who gets what information as it's coming in. Because the two of us may be talking to Google at the same time. How does our router know which information from Google is supposed to go to which one of us?
With the translation, like with the IPS?
Well, what it does is internally it's using port numbers, which is
Okay.
another aspect to the IP number that is going to identify who in the network is supposed to get that information, so it knows which IP to put back on it and send it on. So, all right. So let's clear that. Go. Loading. It's time to climb. I went to the carnival yesterday. Let's go to the Himalayas. Here we go. Go ahead and pause. Go. So we talked about that 169.254 address and why it was reserved. And the main reason it is reserved is for something called a PIPA, which stands for Automatic Private IP Addressing. And what this is a feature on Microsoft to kind of add, they kind of added it to the operating system, and allows for troubleshooting on networks when you're unable to be assigned an IP address. So if I log into the network, the first thing that happens is my IP is 0000, and then I go, and if I'm set up on a dynamic IP, I have the host IP on there, or DHCP server. I'm like, hey, I need an IP so I can communicate. And then it hands me an IP. Well, sometimes it doesn't work. It may be out of IP addresses. It may not be functioning at the moment. In either case, I have to be able to at least function minimally to troubleshoot. And so what the system will do is it will generate what is called a PIPA address. and it self-assigns it. So I did not get one from the network. I assigned one to myself. And so I get a 169.254.0.0 address. As a tech, if somebody is saying they cannot get on the internet, this is one of the first things you need to check is their IP address to see if they have one of these addresses, which would be the 192.254 address, or 169.254 address, excuse me. This allows you to communicate on your internal network, but you cannot go out to the internet. So I can't go to Google or whatnot, but I can DM McLeod and say, hey, you know, are you receiving this? I can send documents to the printer. I can communicate with the server in the office. But if I try to go to Google or, you know, Department of Transportation or any other external website, I will not be allowed because private addresses cannot be routed over public networks, right? But the nice thing is this right here allows me to be able to troubleshoot. Where is the issue occurring? Is it occurring on my NIC card? Because I'm going to get assigned it anyway. So is it happening on my NIC card? Is it happening at the router? You know, where is the issue occurring? So it gives me an opportunity to kind of work and troubleshoot and figure out what's going on. And that's kind of the main purpose of it. It's mostly from a troubleshooting standpoint. Questions on a PIPA? All right. So a PIPA is only one unique type of address. We have different ways we can communicate as well. On the IP version 4, we have what is called a unicast. And the unicast is a direct communication between me and someone else. So if I'm having a direct data exchange between myself and Jamal, that is called a unicast. So it's just me and him communicating. No one else is involved. Broadcast is when I'm communicating with everybody in the network. And how we identify a broadcast is the last address is the highest in the network range. So typically when you see it, it's going to be 255 in that last octet. If you see 255 in the last octet, that is a broadcast address. So anybody who's on that network will get that signal. So I can do it, you know, if I'm internally on a network, I can just hit 255.255.255.255, and it's going to ping it out to everybody inside my network. Or I can direct it at a broadcast in another area. So if I know the network address of our office in Cleveland or whatever, and I want to send, you know, a broadcast message to that group, I can put in their network address, which would be the 172.16.255, and then the 255. Actually, in this case, it's both of them. The 255 would be the broadcast range. Right? All right, we already discussed a little bit what a multicast is, class D. Address. Questions so far? Unicast, broadcast, multicast.
Yeah, my brain phased out for a second. You know, you're broadcasting, or the difference between broadcasting to the network and remotely is what again?
So if I'm broadcasting to my internal network, I would just likely put in this one right here.
Mm-hmm.
So 255, 255, 255, 255. That would be my internal network.
Okay.
And I would hit everything. If I wanted to hit a remote network away from me, like if I wanted to hit my office in Cleveland, I would hit, you know, I put their network in. So this is a /16. So the first two is the network. So 172.16, that's that. So it would go to that network and then hit everyone in that network.
Do you have to specify the 16?
typically, yes. They may request it, but based upon this, it should be known.
Okay. Thank you.
But I would get into the habit of doing that just so that you become comfortable with knowing right off the bat whether something's A, B, or C. All right, IP version 6. So we played around with IP version 4, had those 4 fun groups of numbers, 0 to 255. Oh, those were the simple days. Now we have to talk about IP version 6. Which IP version 6 uses 128 bits, which is represented in 32 characters in hexadecimal form. And they break it up into 8 total groups. Because that is a whole lot of stuff to type in, they give us a compression technique to kind of shorten it up, which some of you may be finding challenges on Coursera with. And so there's 2 basic rules that you need to follow. And the first one is all leading zeros can be omitted. So if you have 00CF, it can be eliminated. If you have like 000D, it can be omitted. If you have 0000 and it's a single field, you put just the final 0, which is the last 0, because it's not leading anything, it's the end of the string. All right, so like in this case right here, it would be just a 0, because all the zeros in front of it would be eliminated, right? And then contiguous fields containing all zeros can be represented with a double colon. This can only occur 1 time. So contiguous fields means 2 groups together of the same, 2 or more. And here we have 3 in a row. And we could do a double colon to represent these 2 right here. Let me do something here. And write this out. Expand this out a little bit here. All right, so I have a IP address here slightly modified to the one we got before. I write this as,
CF.
hold on. Can I write it like that?
No.
Why not? I
you
know the
mi-
rules tell me so, but I've never been a really big rules person. Why would it be a bad idea for me to write it that way?
You cannot repeat double colon.
Okay, but why?
It's the rule.
I'm not a rules person though. Someone needs to explain to me why can, you know, in this scenario, what could happen if I did this way?
Oh, would it be like a loopback address or something?
It's not a loopback address. I know it's not a proper address, but I'm asking why. Why do these things happen? I'm a big fan of why. You know?
Is it because somebody might
For
accidentally omit the zeros in the middle?
Not because some, oh, well, I mean, expand on that, Iman. I think you're knocking on the right door.
No, I'm not.
I
Okay,
was gonna say you can only emit the zeros once.
I understand,
yeah.
but why? Why do we think that's important? So look over here. I have two groups of zeros here. I got three groups over here. Why can't I just condense them together? You know, do the double colons and stuff. It saves me so much typing.
I think then you wouldn't have
To
the,
complete the 8 field.
because that's 3 zeros looping into group into just 2 dots, so that wouldn't be correct. You still wouldn't have the full 16.
Well, I mean, it would. I mean, if I'm just eliminating the groups of zeros, that's all I'm doing. Right?
Can
But
you
you
confuse it for
eliminated
another address?
No, but you have eliminated 3 groups of zeros to the right. So then how would we know where 1, 2, 3, 4 would be?
There we go. The reason we don't do double colons, look at this scenario. So I have 2 groups over here in this double colon. I have 3 groups over here in this double colon. Now, looking at the fields, all I would know is we have 5 groups of missing zeros. Which zeros go on which side? How many go on each side? That would drastically change my IP address, right?
Mm-hmm.
So the whole reason we only do it one time is so we know exactly where the missing zeros go. Because right here, I could put 3 groups of zeros in the front and 2 in the back. That'd go to a totally different location than if I put 2 groups of zeros in the front and 3 in the back, right? So the whole purpose of why we do that is so that we know exactly how many groups of zeros are missing and where they go. So we can only do it one time. Now, if we only have one group of zeros there, so there's only one group of 4 zeros, then we just put a single 0. We don't use the double colon for a single batch. That's where a lot of you may be running into the wall on Coursera, because you see the group of 4 zeros, and there's no other place you can use the double colon, so you go ahead and use the double colon there, and it says it's wrong. Try it with a single 0 in there. Because right there it says contiguous groups, meaning it has to be 2 or more. Right? Does this make more sense? All right. We can use subnet masks on here as well, depending on the network you're on. They typically just use the / notation for it. And the maximum that can be is /64, which is half of your IP version 6 address. And then a special address that we need to know is our loopback, which is : : 1. Which basically means all of them are zeros, and then you only have 1 at the very end. Any questions on this? So 8 fields of hexadecimals, broken up by colons. And if we see anything above an F, like a G, H, I, J, or K, instantly we know it is an invalid address. Because you need to be able to look at a compressed IP version 6 address and immediately tell whether it is real or fake. Why? Because they're definitely going to ask you that on the exam. Anything above F. So A through F is okay with regards to letters in the IP version 6 with hexadecimal, but anything above F, so G, H, I, J, not good. All right. All right, so within the TCP/IP IP version 6, there's a few different types of addresses we have to pay attention to, just like on IP version 4, we had, unicast, multicast, and broadcast. We have similar ones going on in the IP version 6. So, but unicast is kind of split up into a few different ones. They have the global unicast, which is a global address, and it can be routed over the internet, and most of those begin with the prefix 2000. That's a global unicast. Link local unicast. This would be used for communicating within nodes in the same link, so like on your same network or what have you. And most of those begin with FE80 and have a /64. So link local, definitely remember this one. This one comes up a lot. Link local, FE80. That's your first block in your IP version 6. And then unique local, which would identify a specific site within a large organization, usually starts with FC00, and that'd be ULA or unique local, or FD00. And those are all your unicast addresses. So point to point. Multicast is basically the same. And they have anycast, which is used by routers. And this identifies multiple destinations and packets, and they're delivered to the closest destination. So kind of how the internet works is all the routers kind of know who's connected to them. So they know the connections to all their neighboring routers. And then they may have ideas as to who's connected to those neighbors. And so if I'm trying to send a packet to California and I'm here in Jacksonville, I may send a packet to Atlanta because I know Atlanta has a connection to Dallas, and then Dallas would be on the way to California. And so it's how the network is mapping out is through your routers. Does that sort of make sense? And so they use the anycast to kind of figure out who's connected to them, like who's neighboring them. And then they can request the data as to like basically who's connected to them. So they know at least 2 steps. And through that, we can connect or create multiple connections to the same location. Like a mesh network, right? So when you send a bunch of packets to a destination, they're not necessarily all going to follow the same path. They're going to try to get there as fast as they can. Some may go like from here to Atlanta to Chicago. Some may go from like here to Charleston to Memphis. Some may go from here, Tallahassee to Dallas. So they may travel different paths to get there because it would be a more efficient way to transmit the data. And then when they hit the other end, they get reassembled and built back into the data that they were meant to transmit. All right. How do we get the IP address? All this kind of fun stuff. Well, there's 2 ways we can do it. First, easiest in theory is the static addressing. That is, you or I or the IT professional, what have you, going in and manually entering IP address, subnet mask, DNS server, and gateway router. We manually go in, put all that information into every device that's on our network. Seems great until you start talking about really large networks. Then it's a lot to maintain. But we still use it to a minor degree with certain network devices that we do not want to change the address to. We don't want our gateway router to change, to move around, right? That'd be a problem. We don't want printers to change because these are network services that we're utilizing. If we don't want our data servers, our web servers, our email servers, all that stuff, those things would have static addresses and not move around because it's easier to locate those things. So we would actually do something called reserving those addresses for them within our address scope or pool, because we only have so many addresses we can work with. So that's the static addressing. Now, the other way we can do this is called dynamic addressing, and we utilize something called the DHCP server, which is Dynamic Host Configuration Protocol. And basically, we reach out to this server. It is given a scope of addresses. So you basically go in and say, okay, here is 1,000 addresses that you can hand out. And what happens is I plug into the network, I reach out to the DHCP, I say, hey, can you lease me an IP address? And so, okay, it'll hand me an IP address and say, okay, this IP address is yours. It's good for 1 month. So I create a lease with the DHCP. If I am unable to connect to it, that's when a PIPA comes in, at 169.254 that we talked about, and then I can try to figure out what's going on. Yes, Andrew.
This DHCP, it's I forgot, it's the routers that hold IPs, and then when you connect to that router, it gives the IP out to the device, right?
Basically, yes.
Okay, so just talking about that. Okay.
So that's what it is. It's like I connect to the gateway router, like I go on the network and I kind of start shouting out, doing like, hey, I need an IP, I need an IP. And the DHCP server just kind of comes in and goes, yep, I got you covered. Here you go. And it goes ahead and hands that IP to me that I'll use for a predetermined amount of time. Now, the range of IPs that it's allowed to hand out is called its scope. So it's not just randomly generating IPs and just, throwing numbers together and handing them out to everybody. No, there is a range that we will establish for it to hand out. And that range may be different depending on where we're hooking up to the network. So based upon what ports we're using in the wall, like what, on the switch. So what ports we're hooked up to in the switch, those, when we talk about the virtual LAN, where we could take the groups and it's like chunk out HR, chunk out accounting, all that stuff, and make them completely different groups. How we would determine those different groups would be how they're going into the switch, and then they would have different IPs for routing. And so we would say, here's your routing, or here's your IP range for HR, here's your IP range for accounting, and so on, based upon how they're set up. And the DHCP is what would handle all this out. Now, remember how I always said that the IP address is only good for like a month? Once that month is up, you turn it off, you turn back on, your lease is expired, you have to re-request an IP address and it come back to you. And then it'll give you a new one. So it'll renew your lease or give you a new lease or something like that. We can adjust the time of how long that this lease is. So you ever been to a restaurant that has free Wi-Fi, like, Starbucks or something like that? What do you think is going to happen if they are handing out IP leases with a 1 month lease? What happens? What do you think might happen with that? Every single person coming in gets a 1 month lease on there.
Yeah, not everybody's gonna, any new customers would have it for so long that continuously there wouldn't be any more for much
We'd
people.
run out, right? We only have so many to give out. If we're giving them for a month and these people are, we get thousands of customers a day, right? If, 2/3 of them are using the internet access when they come in and we're handing out IPs to them for a month, that's a problem, right? So what we can do is we can shorten that time in a scenario like this to a couple hours. So say you would have an IP lease of 4 hours. So they come in, they get their coffee, they drink their coffee, they leave. After a couple hours, the DHCP service is okay, that lease is revoked, they're done, they're gone, and then they can hand out those IPs again. So we're able to cycle those IPs a lot faster. If the person has been sitting there for an inordinate amount of time drinking coffee and their IP expires, then they can just request a new one and it's no big deal. But we don't run out. So that's going to be drastically different than an office of like 20 people who maybe has an occasional salesman come in once a month or so. We can have IP leases much longer because it's not really drastically changing, right? So we have to pay attention to the fact that we have leases, and then those leases, have specific time frames. All right, 1 second here. All right. So that's our DHCP. This makes our life a lot easier because we don't have to individually go in and assign every unique IP to every single network device that is on our network, which is awesome because we have other things that we have to do with our day. So if you have thousands of computers, this would be exceedingly tedious to do. But the key pieces of information that are needed if we are setting up a static one are our IP address, the subnet mask to which we're going to use, default gateway. So how do we get out of our network? So that'd be our edge router. And then our DNS server. Which is kind of like our internet phone book. And then occasionally you may need to use the Win server for intranet use, but that is more enterprise. Yeah, if the DHCP is not functioning properly, it can be weird. So from our network, right click, go to properties, it'll bring you into your general. You can see all of your network properties here. You go to your IPv4, click on it, hit properties, and it'll bring you into the main one here. And you can practice this on test app. Because there's a lab for that. So our gateway, this is the router that is basically located on the edge of our network. That is the breaking point or the demarcation point between our internal and external networks, our intranet or internal, or internet, the external internet. And we already talked about the network address translation. The router itself translates your IP to a public form so that it can be routed over the public internet from your internal private address that you are likely using. All right. So,
Kelly,
When
could
we
you go
get
back
up-
one slide for 1 second, please?
yes, absolutely, I can.
Thank you. Got it.
All right, so we get to the outside world. How do we know where we're going? It's much bigger, scarier. There's people out there wanting to look at our data. So we utilize what are called FQDNs, or fully qualified domain names, sometimes referred to as URLs. And these are the web addresses that we communicate with on a daily basis. So like www.google.com is an FQDN, or fully qualified domain name. Well, Google, like the computer or the routers or whatever, don't necessarily know what Google is. What they need is an IP address. That's how they route traffic. So that's kind of like a phone number for the most part. So we got to call the phone number, but we, being the humans that we are, it is hard for us to remember a long string of numbers. It is much easier for us to remember a couple words put together. So what we utilize is something called the DNS, or Domain Name System Server, DNS. And what this does is resolve our domain name to an IP address. So we send the domain name up, it goes up and says, okay, this is that website. Okay, here's the IP address for that website. Boom. Now it can be fired off into the internet and know where it's supposed to go. Good way to think of a DNS server, we carry one around with us everywhere we go. Our phones. When we go into our phones, we say, call mom. We don't say, call 555-2121. But when we say call mom, our phone can go through our contacts, hits the contact. In the contact information, it gives me a phone number. and then it can dial that phone number and get it out to the internet, right? So our phones can operate like a personal DNS server for us, for all the contacts that we use. Similar process. The DNS is like a phone book for the internet. When we type in a web address, it goes there, gets the IP number it needs to communicate with, and then fires it out over the internet. We can type in the IPs as well and go right where we want to go. So like if we want to talk to the DNS server for Google, we can do the www.google.com. Or we can type in 8.8.8.8, and it'll take us right to Google. That's their DNS server name. So that is its main purpose, just to work as a phone book for the internet. Any questions on this? Yep. So for those who are wondering, try going into your command line at some points. So do your CMD, go into your command line, type in ping space www.google.com. It'll send packets to Google and send it back to you. And then do the same thing, ping space 8.8.8.8, and you'll send a ping to Google's DNS server, and it'll send you information back. So one way to do it. And this is something we can also use for troubleshooting our DNS server. So if I can ping 8.8.8.8, but not ping www.google.com, that means there's something wrong with my DNS server. It's not able to translate the FQDN I give it to an IP address. So if I can hit the IP, but not the web address, something's wrong with my DNS from a troubleshooting standpoint. All right. Questions so far? Binary counting. I know you guys, really missed this when we were doing it. One of the easiest ways to count in binary, if you need to, is to just draw out this chart. It's a base 2 system. It doubles every time. So 1, 2, 4, 8, 16, 32, 64, 128. That gives you an octet. And then how we add it up is we kind of put a hash under here for each number that we're going to add up to get to the number we want to get to. And y'all are sitting there going, maybe, is there a way we can practice this other than the one question or quiz that we had on Coursera? Want more practice. I want to be able to see binary in my sleep like Neo. We have a spreadsheet that'll help you out with that. It'll kind of help you understand IP addresses a little bit better and how binary counting works. So in this little spreadsheet, I'm going to give you a link to it, and you just make a copy for yourself so you can use it. You can start adding up numbers in binary. So boom, 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 boom. And so we have 1 0 1 0 1 1 1 0. The binary for it reads out in the green bar, gives me 174. So you can practice trying to count in binary and have a better understanding of it. And you can do entire IP addresses in it as well. And if you come into other tabs, you can create IPs. It'll tell you whether it's a network A, B, or C, how many hosts you have, and all that fun stuff. Even gets into your CIDR notations, which we'll talk about on Monday. All right, we go back to the main IP here. Grab the link for you guys. So when you get in, please do not edit this one. Just make a copy for yourself. And then you can play around with it. But it'll give you some practice in working with binary. Try to give yourself a random number between 0 and 255 and see if you can just create it in binary. True. Yeah, I didn't think of that. But either case. So that is our counting in binary. We've done it in Coursera. We've done it with hexadecimal yesterday when we were doing Flippy Bit and all that fun stuff. So and there's Flippy Bit again.
More Flippy Bit?
It just comes up from time to time to remind people, hey, you can still play if you want. All right, TCP versus UDP. So there's different types of transmissions that can go over the internet. One is a connection-oriented, one is connectionless protocol. And we have different times in which we would want to use this. So TCP, connection-oriented, means whatever I'm sending you is very important, and I want to make sure that you received the data. So it's going to do data checks from time to time and say, hey, what have you received? And then, like, so if I sent you 10 packets, it's going to go, hey, what did you receive? And you can be like, okay, I got 1, 2, 3, 5, 7, 8, 9, and 10. And then it goes, okay, I'll resend you 4 and 6, and it resends 4 and 6. So that's connection oriented. And TCP obviously stands for Transmission Control Protocol, and it used something called the three-way handshake to initiate a connection. So you have the SYN, or the synchronizing, or SYN. So it sends a sync packet. It says, hey, I want to talk to you. And then the host computer will go SYNAC, or synchronize acknowledge, send it back to you, and then you would go acknowledged, and then you would start transmitting. So it's called a three-way handshake. Predominantly used by things like web servers, email, stuff like that, where we're going to be receiving data, documents, stuff like that. And then there's the counter to this, which is UDP, which is connectionless, and it's under what's called best effort. And so you request a piece of information and it just starts firing away, and it does not care whether or not you receive it. So it just keeps sending, keeps sending, keeps sending, and you're trying to grab as much as you can and put it together. The best explanation of this is like streaming video. So if you're watching, you ever watching TV and you see it start to pixelate and you get those little boxes and artifacts and stuff in the screen, and then eventually it cleans up. Well, that was data packets that were getting missed, is basically what that is. Now, here's my question to you. Do you care if your, streaming box or whatever you're using sends back an error message to get those pixelated boxes from about 20 seconds ago?
No.
No.
No. You want it to do its best effort going forward, right? So rather than chewing up data, trying to correct things that happened a few moments ago, give me the best you can going forward. And so that's what they mean by best effort. It's just firing away and you're trying to gather and hold on to as much as you can. So Zoom calls, it's UDP, right? Voice over IP, it's UDP. If the voice starts to go all robotic and pixelate, you don't really care if it's going to go back and fix that data issue from 30 seconds ago. You want to be able to clearly hear what's going forward. So that's kind of the difference between the two. One is for data integrity, and it's going to verify that the data has been sent and received. The other is best effort, and it's usually for streaming data, something along those lines where you're just trying to get as much as you can of it. Make sense? All right. Here we go. Network sockets. So these use programming requests that are called APIs. And it's kind of how we connect between two different protocols and how we know what type of communication we're going to be looking, to have. So if I'm trying to connect to a web server, I don't want to use email protocols, do I? So if I'm going to Amazon, I don't necessarily want to use email protocols. If I'm going to try to put in my password, I don't want it to be on a unsecured web server. So we want to determine what type of socket or port we're going to be using, and that's going to determine our communication medium, or protocols we're going to be using when we talk. And how this can be notated on a IP address is you have a standard IP, and then they could have a colon, and then you'd have a port number after it. Right here, you have port 25. That's for email. That's your SMTP protocol. And then you have your web protocol. So I'm going to communicate with a web server, and that colon 80 is my HTTP protocol. So that's my web server. So there are a number of ports on a computer, and we're talking about software sockets versus physical ports on the outside. These are two different things. And there's a number of them we have to know. There's roughly about 65,000 ports on a computer. So any computer you have has roughly about 65,000 ports on it. Thankfully, A+ says we only have to remember about half of them. So we're going to be getting into a few of them today, talking about them, and kind of their importance and what we gotta work through. So depending on the port you're using, it could be a TCP/IP, it could be a UDP, or it could be either. So we're going to get into some of the common protocols that we talk about here. So logical ports that we do need to remember. We do have an acronym that'll help you remember a group of these, or a mnemonic that'll help you remember a group of these. But these are the primary ones that we're going to be interfacing with or talking about on a regular basis. They come up all the time. Yes, we do need to know this. Please take screenshots, write it down, flashcards, whatever you need to do. So the first one is FTP, or File Transfer Protocol. It is what it says it is. It is a way to transfer files between two computers. And that is ports 20 and 21. Why it uses two ports, we'll explain a little bit more when we talk about something called port triggering, because this is an older port protocol. Next, you have an FTP. Typically is open air. So basically what is being transmitted is openly visible. Transmits what's called clear text. Next, we have secure shell, or SSH, that is port 22. And this is used to pass in your login information to a remote computer so that it at least has a base level of encryption on it. So it's not an open air communication. Port number 23, another old one, Telnet. It allows you to control a computer remotely. This is also open text, or clear text, so whatever is sent is able to be viewed to anybody watching on the line. And this is port number 23. And my old partner used to say how you remember this one was, 23, Michael Jordan, that was his number. And so Telnet to the net, Michael Jordan. So port number 23. Number 25 is our first email protocol, and this is SMTP, Simple Mail Transfer Protocol. This is used to send email messages. Easy way to remember this, SMTP, send mail to people. Simple Mail Transfer Protocol, send mail to people. Number 25. All right, number 53, that is our DNS, which we just talked about. This translates our fully qualified domain names into IP addresses. That is number 53. I'll wait here a second while y'all get some screenshots.
So what's the difference between the port number 23 and port 3389?
They use different communication protocols. So 3389 is a Windows specific remote desktop, where Telnet is a little bit lower level protocol. So it's going to be operating more on like your Unix DOS levels. It's like more command line.
Okay, thank you.
Is that the same port number that a lot of basically scammers use to access people's computers?
Yes.
Interesting.
A lot of these ports are ones that scammers will use. And one of the things you need to look for is ports being used, like in the security perspective, you have to look at ports being used in a manner in which they're not supposed to be. So like if somebody is trying to do a remote connection through a HTTP port, they're trying to essentially use a port in a manner in which it's not intended. So they're trying to bypass security by doing that. And one of the first things hackers will do is do what's called a port scan on your computer. They will scan all the ports, like ping every port, and try to find open ports that they can try to manipulate.
When you say open port, does that just mean an unsecured port?
Well, you can have ports left open, basically waiting for some form of communication.
Oh, okay.
And, you know, like, so if you're trying to connect to like a web server, they're going to have port 80 open for HTTP because they're expecting communication to come in on that port. Now, a standard computer that hasn't been adjusted or anything like that, a lot of your standard ports are going to be open to wait for some kind of communication. So something that has to happen is called system hardening, where you're going in and closing off any ports that may or may not need to be used, or that may not or should not be used by that machine. And you go through and close off all those ports so that communication cannot happen through those ports.
Do all computers have system hardening?
No.
Oh, okay.
In fact, most do not.
Are there common ports that these scammers would use specifically?
Yes, all the ones we're going over right now. There's a lot of ports that they use. Yes.
So this is also a lesson on how to protect ourselves.
Yep. But again, these are well-known and commonly used ports. So as just a standard user at your home, a lot of these ports, almost all these ports are going to be open on your system, because they don't know whether or not you're going to use your computer to set up a website or do all that stuff. So it's just, they're standard ports are kind of open. You would need to go through and do system hardening and close off things that you do not want accessing it, or ways you do not want your system to be accessed.
I have one more quick question. How do we go about closing these ports? Like if it has a connection already, how do we go about terminating that connection?
We have the kill commands to kill any protocols that are currently running that we are not authorizing. And then there are ways we'll get into later about how to close them off. So. All right, other well-known ports we need to be aware of. I can feel y'all's paranoia starting to rise a little bit. We haven't even got to security yet. So other well-known ports we need to be aware of. HTTP, this is Hypertext Transfer Protocol. This is the basic web communication protocols. Like when we go to Google or we go to Amazon or we go to, a lot of other places, we're using HTTP protocols for the most part. That is port 80. Next, we have POP3. This is our second email protocol. And this is a way we would receive emails. So SMTP was the way we would send email. POP3 is a way we would receive email. And that is the Post Office Protocol, or POP. It is an older port, and there are slight differences between it and IMAP, which is our last email protocol, which is 143. And there's the Internet Message Access Protocol, another way we would receive messages. All right, last two, you have RDP, which is Remote Desktop Protocol. This is another way we would remote into somebody else's computer. It is a Windows based system. And this is the more common one used nowadays by IT to remote into computers to, perform some form of assistance. And by scammers to kind of get, get you to allow them access. And then lastly, you have the Apple filing protocol, and then it is obviously an Apple proprietary. It is for sharing files and folders and stuff like that. So there's a few others we'll need to know, but these are the main ones that we want to kind of keep in mind. Here we go. All right.
So Apple wouldn't use FTP, they just use AFP.
Sometimes, yes.
Okay.
All right, if you need to know DHCP's port, that is 68 or 67, as we just talked about. DHCP is our network protocol. That's how we get our IP addresses. LDAP, it's the lightweight directory access protocol. This is kind of like it's like a lightweight phone book for network resources. Like if I'm going to go communicate with, let's say Generation or whatever, I'm going to communicate with Generation and I need to get in touch with, Andrew in my class. So I would connect to the LDAP, and then the LDAP would tell me, here's how, here is the web information or the access information for Andrew. So it would be kind of like a little bit of a phone book. Or if I needed to know how to access a network printer, or if I needed to go know how to get to the email server, all of that information would be kind of in this little directory access. So all network resources and stuff like that would be in the LDAP. And that is port 389. SNMP, we don't get into this a lot in A+. This is a way for you to kind of manage network resources remotely. So like if I wanted to hook into my managed switch, if I wanted to communicate with my router or something like that and download logs or any of that stuff, I would use the SNMP protocol. The important part that you need to remember about SNMP is they always throw that in as a possible answer when the answer is SMTP. Because it's close enough in appearance that people will confuse them. So send mail to people, not the same as the simple network management protocol. All right, questions so far? All right, server message block. This is another Microsoft protocol used for reading and writing files and to request services from a server program. Port number on this one is not overly important, but it's 139 for those who are looking for it. We talked about secure shell already. Then you had SFTP, which is using secure shell for a file transfer protocol. So it's secure file transfer protocol, and the port is the same as SSH, so it's 22.
So you said port 32?
22. It's the same as secure shell. So it's the same port number as SSH. So typically when you're transferring files, that's the one you're going to use is SFTP. If you're going to use the protocol, you're not going to just use a standard file transfer protocol if there's any sensitive information on it. All right. Here is a quick breakdown of the OSI layers. Kind of shows you the protocols that are being used in the process. This over here is kind of a good representation of the Google model. So you have the upper layers, which is 5, 6, and 7 combined into an application layer. And then it gets you down into the type of data that's on here. You get the segment, the packet, the frame, and then breaks it down into bits going out over the internet. So good one to kind of have a screenshot of.
Real quick, it's important to know the names of what's being like retrieved, because I in the transport, which is it's the IP segment, right? That's what it's called.
Mm-hmm. It's IP packet,
So-
packet, and network segment, I believe is what they call it,
Okay.
or network frame, IP packet, TCP or UDP segment. And internet frame. Here's some public Class A addresses if you're interested, but that'll be on the student pace if you want it. We already talked about virtual LANs when we were going over switches. And this is kind of what it would look like. So if you had like 12, you can see you have VLAN 1, which would be one network. That would be like port 1, 4, 5, and 12 on the switch. And then they had, VLAN 2, which would be group 2, 8, and 10. And then VLAN 3 would be 3, 6, 7, 9, and 11. And all of these would be viewed as like VLAN 1 would view itself as one LAN and could not talk to somebody on VLAN 2 unless they went to a router first and then were routed back. Because they're viewed as being on different local area networks. But it's being done virtually through a managed switch, allowing you to break up those ports into smaller and smaller groups as needed. So it's a good graphic to kind of illustrate it.
What is this trunk?
The trunk would be like the basically it'd be like the Ethernet cable between the two. So if you had multiple networks and the trunk, that'd be like a primary communication line. So if I was setting up multiple floors and I was using a bus to connect the floors, so a bus network segment to connect a bunch of star networks, and in between floors I wanted to have extremely high speed, I would use like fiber optic lines for the trunk, so the communication medium between the switches.
Okay, thank you.
So it could be an Ethernet cable, it could be, you know, a coaxial, it could be a fiber optic, but it's basically the means by which you're connecting these two. But typically it's going to be a high-speed communication or a high-speed line. All right. VPNs. Anybody here use a VPN? Couple. All right. I think I've recently, or I mentioned it briefly before, recent legal cases have come up and, you know, presided in court. And basically the agreement of the court is if you are making no efforts to encrypt your data, it is fair game. Meaning they don't have to go to a court and get a warrant to search your data. They don't have to have any kind of special permission. They can literally just go to your ISP and say, hey, give me all of Justin's data. And the ISP will go, okay, here you go. So if there is no effort to encrypt your data or hide it, there is no expectation of privacy. So these are legal cases that have been presided recently. So take that in mind. VPNs, what they do is they do a couple of things. They create what's called an encrypted tunnel for you to communicate, and you would go into their network. And then you could pop out somewhere else. So you could pop out in Asia, you could pop out in Europe, you could pop out somewhere else in the United States. Like I could look like I'm in Illinois or in, you know, Nebraska or New York or, you know, Texas or, you know, Michigan or what have you. So I can make myself appear as if I'm somewhere else regionally different. This works if you're trying to get beyond what's called regionally locked material, like if you have a Netflix account or something like that. Going to make yourself appear like you're in Canada and you go look at your Netflix, you're going to have very, very different stuff available for you to watch than if you tried to watch it here in the United States, because there's regional locks on material. So VPNs can do that. And what they do is they encrypt the data to and from their network. So from where you are to where, you know, their network begins, and that would be the closest server farm to you typically. Even your ISP would not be able to see that data. It would be encrypted even from them. Not all VPNs are created equally. Some are what are called half tunnels, meaning they only encrypt either the upstream or the downstream data. So the other half of the data is not encrypted, and they do that because it makes it process faster. It's you know, your data speeds aren't as heavily affected by it, but it's significantly less secure. Other ways they can do it, or what it's used for, is a company could have a VPN. So say someone like me, I'm working remotely for Kingsborough College in New York. I live in Florida. Because of the way they have their system set up, I would not have access to the resources on campus because I'm viewed as being somewhere else. I'm in Florida. So I actually have to use something called the VPN. I would have to connect to their VPN, which creates that encrypted tunnel and gets me to their network. And then I pop out inside their network. So all the network resources view me as if I'm physically there. So it allows remote people to gain access to protected information in the company because the local systems will view them as if they're a local machine. So companies can set up local VPNs in order for remote workers to be able to gain access without having to open themselves up necessarily to greater threats. Make sense? Just from a basic level. All right, we'll talk about VPNs a couple more times throughout the course, but it's just a basic explanation as to kind of what's happening. Here's the mnemonic that we use. And basically what this does is it lays out all the ports in ascending order. So lowest ports at the top, you know, biggest ports at the bottom. This is what I use to help memorize the ports for this group here. And it's for safe technicians. Simple deeds help put immature hackers at rest. So you may be able to, like if you're writing them down, you may sit there and go like, okay, I know what SMTP is, and I know what HTTP is. So SMTP is 25 and HTTP is 80. What's DNS? Well, I know now that DNS falls in between 25 and 80, and that'll at least help me get close enough to try to remember. Right? I don't know how to take that statement, Shante. All right. So everybody get a screenshot of this. It's just a real quick, easy way to kind of know it. So certain things that I mentioned to y'all that I write down regularly. I wrote down regularly until I memorized them. One was the RAID arrays, if you remember that. So I wrote down the different types of RAID until, they started to become second nature, and I understood how they were laid out in the, what's the minimum number of drives, what's my redundancy, and all that kind of fun stuff. The other thing I wrote down was my ports, because there are a lot of questions where they're going to use ports, and they may give you the port acronym, and you have to figure out what the port number is, or they may give you the port number and you have to know what protocol they're talking about. So it can go different ways. All right. Any questions on this? All right, just in time. We should now be able to explain the purpose and role of the TCP/IP in the internet or private network. Explain characteristics and properties of TCP/IP. And then some common TCP and UDP ports and protocols that we would interact with on a regular basis. Questions, comments, concerns? All right.